Hello students, today we discuss about the IEEE standard for floating point format. There are two formats, one is single precision and the other is double precision. The IEEE floating point formats, they are widely used in many modern digital signal processing applications. The two formats are numbered as IEEE 754 standard. The first one is IEEE single precision format and the second one is IEEE double precision format. First we describe the single precision format. As shown in the figure, we observe that the total length is 32 bits, of which the most significant bit is the sign bit and the next 8 bits are the exponent bits and the remaining 23 bits are the fractional bits. So bits numbered from 0 to 23 are fraction, bit number 23 to 30 is exponent and 31 is the sign. To convert the number in IEEE format to decimal, the formula that could be adopted is shown here. So the result will be called as x. So x is said to be equal to -1 raised to s, where s is a sign bit. This yields an answer which is positive in case of the sign bit being 0 and negative if the sign bit is 1. This format has an implicit value which is 1. The value which is following the decimal point will be the fractional part and the exponent is 2 raised to e minus 127. In IEEE single precision format, the 23-bit fractions are f, 8-bit exponents is e, and 1-bit sign bit is s. The total number of bits for each word is 32 bits. The mantissa happens to be lying in the normalized range of +1 and +2. The sign bit s is used to indicate the sign of the number. S equals to 1 is negative, s equals to 0 is positive. The exponent is expressed in excess 127 form. The value of 127 is an offset for the 8-bit exponent ranging from 0 to 255. Then e minus 127 will happen to have a range which is in between -127 to 128. This formula can be applied to convert an IEEE 754 standard single precision number to the decimal number. So once again, we're having a look at the formula here. So this formula is needed to be applied to a number which is shown here. And this number is in the IEEE single precision format. Now we understand that the most significant bit is 0, hence the sign should be positive. The 8 exponent bits are captured here, and when you change it to decimal, the equivalent is 128. The remaining bits which are contributing to the fraction part, it is equivalent to 0. Hence, the number will be -1 raised to the sign bit 0 multiplied with 1 which is implicit whole number part, 0.0 which is the fractional part, into 2 raised to 128 is the exponent that we got, minus 127, which results in the answer which is 2.0. Similar conversions can be carried out for the numbers which is shown below. The example below is again for a positive number, but the exponent and the mantissas are different than the previous example. On substituting the value, we obtain that the fractional part here is 0.101 and the exponent is 129, yielding an answer which is 6.5. A similar combination with the sign bit as 1 should give you a negative number. So inserting the value minus 1 raised to 1 gives an answer which is minus 6.5. Let us consider an example of the number in IEEE single position format to be changed to the decimal format. Now, as we are aware of the bit pattern, we identify that the sign bit, the exponent, and the fraction. So sign bit here is 1, the exponent is said to be 2 raised to 7, which is 128, and the fractional part is 0.01. So the following decimal number can be expressed by using the conversion formula, and we get the result as minus 2.5. Now, in conclusion, the value x represented by the word can be determined based on the set rules, but the rules have certain exceptions. The exceptions are as follows. If E values 255 and F is non-zero, then X is said to be not a number. For the same combination, when F is 0 and S is 1, then X is negative infinity. If S is 0, then X is equal to positive infinity. With E lying between 0 to 255 and X being given by this, when one point F represents the binary number created by prefixing F with an implicit leading 1 and binary point. These are the rules that we apply. If E value is 0 and F is non-zero, then X will yield this particular value. This is an unnormalized value, and so on. And here is some situations showing these exceptional cases where we got the answer as 0, minus 0, infinity, minus infinity, not a number, etc. And here is the representation of the smallest positive value which can be represented. So we get the smallest positive value by taking the most significant bit as 0, all the exponent bits as 0, and the mantissa having the least significant bit as 1. Now this combination gives you the answer, which is 2 to the power of minus 149. We can see the numbers which are falling in the range of 2 to the power of minus 126 and 2 to the power of minus 127 also. Next, moving on to double precision format. This format is described in the figure which is shown below. We observe that double precision has twice the length that of single precision. So it is composed of two fields which is 32 bit each. Total length will be 64 bits. The IEEE double precision format standard representation requires a 64-bit word which may be numbered from 0 to 63, starting from the left going towards the right. The first bit happens to be the sign bit. The next 11 bits are the exponent bits. The final 52 bits are the fraction bits. The IEEE floating point format in double precision significantly improves the dynamic range of number representation since there are 11 exponent bits. The double precision format also reduces the interval size in the mantissa normalized range between +1 and +2, since the total 52 mantissa bits are available in comparison with that of single precision, which has only 23 bits. Now we can apply the conversion formula in a similar pattern to how we did it for the single precision case. Here we are showing the 64-bit as two registers composed of 32-bit each. So this is called as the even register, this is called as the odd register. The conversion formula can be observed, which is quite similar. -1 to the power of sign bit plus 1 point, the fraction part, 2 raised to the exponent minus 1023. So the number here, exponent, is in excess 1023 format. As an example, we look at the number in IEEE double precision format, and this has to be converted to decimal. The conversion formula procedure would be same as the previous. So the sign bit is the most significant bit, it is 0. The exponent, when we locate it, yields a value 2 to the power of 9. Equivalent of that is 512, and the fraction part here is having the value 1, 1. So hence its equivalent is going to be 1.75. So using the formula, conversion formula, we do the substitution. The value is going to be 1.75 into minus 1 to the power of 0 because the number is positive, and the exponent 512 substituted here will give the answer as minus 511. This can be adjusted and the result ultimately you will get is something like this. Now, similar to the single precision case, here also we have certain exceptions and rules which are used to represent the numbers. We have rules for not a number, negative infinity, positive infinity, how to calculate the value and what range should be the exponent, and the numbers which are unnormalized and representations of minus 0 and plus 0 respectively. Thank you all.